Within the human body, beneath the steady rhythm of breathing and the quiet beating of the heart, there exists a constant and gentle flow of electrical activity. This activity does not announce itself loudly, nor does it demand attention. Instead, it unfolds continuously, shaping sensation, movement, thought, and rest with remarkable subtlety. Electrical signals are not foreign intrusions into the body, but natural expressions of living tissue, arising wherever cells maintain boundaries, balance, and connection. To understand this inner electricity, it helps to release the idea of sparks, shocks, or dramatic surges. The electrical language of the body is calm and measured, more like a slow tide than a flash of lightning. Every moment, billions of cells maintain tiny differences in electrical charge between their inner and outer environments. These differences are not accidents. They are carefully sustained states that allow cells to respond, communicate, and adapt. Life, at its most basic level, depends on separation. Each cell is enclosed by a thin membrane that distinguishes what belongs inside from what remains outside. This boundary is not rigid or impermeable. Instead, it functions as a selective interface, allowing some substances to pass while holding others back. It is along this boundary that electrical properties naturally emerge. When charged particles are unevenly distributed across a membrane, an electrical potential arises. This potential is not a metaphor, it is a measurable physical condition, as real as temperature or pressure. In the resting state, most cells in the body exist in quiet electrical balance. Their internal environment carries a slightly negative charge relative to the space outside. This difference is small, but it is meaningful. It represents stored potential, a readiness rather than an action. Much like a still lake reflecting the sky, the resting electrical state of a cell reflects stability. Nothing appears to be happening, yet everything is prepared. This quiet readiness is especially important in the nervous system, where cells are tasked with communication across distance. Neurons, the specialized cells of the nervous system, rely on electrical signals to transmit information efficiently. However, even neurons spend most of their time at rest. Activity is brief and purposeful, emerging only when conditions call for it. The majority of neural life unfolds in silence, held in balance by the careful movement of ions and the patient work of cellular machinery. The ions involved in this process are simple elements, familiar from chemistry and nutrition. Sodium, potassium, calcium, and chloride move in and out of cells through specific pathways. Each carries an electrical charge, and their distribution determines the electrical state of the cell. Specialized proteins, embedded in the cell membrane, act as channels and pumps, guiding ions where they are needed and maintaining gradients over time. These gradients require energy to sustain. This ongoing effort underscores an important truth. Rest in the body is not the absence of work. Electrical stability is actively upheld, moment by moment, ensuring that cells remain responsive without becoming overwhelmed. When a signal does occur, it does not arise from nowhere. It emerges from this background of calm. A small change in the environment, perhaps a touch on the skin or a shift in internal chemistry, alters the balance of ions at the membrane. If the change is gentle, the cell absorbs it without response. If it reaches a certain threshold, the cell responds in a characteristic way, allowing a wave of electrical change to travel along its surface. This wave is not destructive. It is brief, controlled, and self-limiting, returning the cell to rest once it has passed. This principle of threshold and response allows the nervous system to filter information. Not every stimulus becomes a signal, and not every signal becomes an action. The body continuously evaluates its internal and external environment, responding only when necessary. Electrical signaling, in this sense, is a language of restraint as much as activity. It conveys meaning not by constant noise, but by selective expression. Beyond the nervous system, electrical signals play essential roles in other tissues. Muscle cells use electrical changes to coordinate contraction, allowing movement to unfold smoothly and predictably. The heart relies on a carefully timed pattern of electrical activity to maintain its rhythm, beating reliably without conscious oversight. Even glands use electrical signals to regulate secretion, ensuring that chemical messages are released at appropriate moments. Despite their importance, these electrical processes rarely intrude into awareness. We do not feel ions moving or membranes shifting their charge. The body conducts its internal conversations quietly, freeing consciousness to attend to the broader experience of living. This invisibility is not a sign of insignificance. Rather, it reflects the elegance of systems that work so well they do not call attention to themselves. In learning about electrical signals in the body, it can be helpful to adopt the same calm perspective the body itself maintains. There is no need to rush through details or strain to remember terms. The underlying principles are simple and repeat throughout biology. Separation creates difference. Difference creates potential. Potential allows communication. Communication supports coordination. Coordination sustains life. As this lecture continues, these ideas will return in different forms, applied to neurons, muscles, sensory systems, and states of rest and sleep. Each time, the focus will remain on balance rather than urgency, on continuity rather than disruption. The electrical nature of the body is not a story of sudden events, but of ongoing harmony maintained across countless cells. For now, it is enough to recognize that within you, at this very moment, a vast and gentle electrical landscape is quietly at work. It does not demand effort or attention. It simply persists, shaping experience and supporting rest, one small and steady charge at a time. 2. Cells as living electrical units. Every cell in the human body can be understood as a small, self-contained electrical environment. Long before a nerve sends a signal or a muscle contracts, individual cells quietly maintain conditions that make electrical activity possible. This is not a specialized feature reserved only for neurons. It is a fundamental property of living cells, woven into their structure and sustained throughout their lifespan. At the center of this electrical nature is the cell membrane. This thin, flexible boundary surrounds each cell, separating the internal environment from the surrounding fluid. Though delicate in appearance, the membrane is highly organized and remarkably selective. It is composed primarily of lipids arranged in a double layer, creating a barrier that resists the free passage of charged particles. Because of this resistance, differences in electrical charge naturally arise between the inside and outside of the cell. Within the cell, a dense and carefully regulated mixture of water, proteins, ions, and other molecules creates an internal environment distinct from the outside world. The surrounding extracellular fluid has its own composition, shaped by circulation, metabolism, and the activity of neighboring cells. The membrane stands between these two spaces, allowing the cell to preserve its identity while remaining connected to the larger system. Charged particles, known as ions, are central to this arrangement. When these ions are distributed unevenly across the membrane, an electrical difference emerges. This difference is called a membrane potential, and it represents stored electrical energy. The cell does not generate electricity in the way a machine does. The maintenance of this arrangement is not passive. Cells invest energy to keep certain ions more concentrated on one side of the membrane than the other. Specialized protein structures embedded in the membrane act as pumps, moving ions against their natural tendency to diffuse. This process requires energy, usually supplied by molecules such as ATP, which serve as the cell's internal fuel. Through this effort, the cell preserves its electrical readiness. At rest, Most cells maintain a stable membrane potential. This resting state is not uniform across all cell types, but it follows a consistent pattern. The inside of the cell remains slightly more negative than the outside. This negativity arises largely from the movement and placement of potassium ions and from the presence of large, negatively charged molecules within the cell that cannot easily cross the membrane. Together, these factors create a calm but purposeful imbalance. This imbalance is essential. Without it, cells would lose their ability to respond to changes in their environment. Electrical potential allows a cell to sense, to react, and to communicate. It provides a baseline from which meaningful shifts can occur. In this way, the resting membrane potential is less like inactivity and more like quiet attentiveness. Even cells that never transmit long-distance signals rely on electrical properties to function properly. For example, epithelial cells lining the gut or the skin use electrical gradients to regulate the movement of substances across their surfaces. Immune cells adjust their membrane potential as they activate and respond to threats. Glandular cells depend on electrical changes to release hormones or enzymes at the appropriate moment. Across tissues and organs, electrical states guide cellular behavior. The structure of the membrane itself contributes to this electrical character. Ion channels, which are protein pathways spanning the membrane, allow specific ions to move in or out of the cell. Each channel is selective, permitting only certain ions to pass. Some channels remain open most of the time, allowing a steady exchange that supports the resting state. Others open only under particular conditions, responding to changes in voltage, chemical signals. Because the membrane is selectively permeable, ions do not move freely. Their movement is regulated, timed, and often subtle. Small shifts in permeability can lead to meaningful changes in membrane potential. These changes may remain local and temporary, or they may set the stage for more widespread electrical events. In all cases, the cell remains in control, integrating multiple influences before responding. Water also plays a crucial role in this electrical environment. As the primary solvent within cells and tissues, the fluid nature of the intracellular and extracellular spaces ensures that electrical effects are distributed smoothly rather than abruptly. This fluidity supports gradual transitions and protects cells from sudden extremes. Importantly, electrical properties are inseparable from chemical ones. The same ions that carry charge also participate in chemical reactions, influence enzyme activity, and help regulate cell volume. Electrical and chemical processes unfold together, each shaping the other. This integration ensures that signaling remains coordinated with metabolism and structure. As cells grow, divide, and age, they continuously adjust their electrical states. During development, changes in membrane potential can influence cell differentiation, guiding cells toward specific roles. In healing tissues, electrical gradients help coordinate repair. Even in mature, stable tissues, subtle electrical shifts reflect ongoing adaptation to internal and external conditions. What emerges from this perspective is an image of the body as an immense collection of living electrical units, each maintaining its own balance while contributing to a larger whole. Cells do not operate in isolation. Their electrical states influence their neighbors through shared fluids and direct connections. In some tissues, specialized junctions allow ions to pass directly from one cell to another, creating coordinated electrical fields across entire layers of cells. Yet, despite this interconnectedness, the system remains remarkably stable. The body avoids chaos by grounding electrical activity in structure and regulation. Boundaries are respected, thresholds are maintained, and energy is carefully managed. This disciplined organization allows electrical signaling to remain precise and reliable. As you rest and listen, it may be comforting to recognize that this vast electrical network is quietly supporting you without effort or awareness. Each cell holds its charge patiently, ready to respond but content to remain still. It is the steady condition that makes life possible. In the next part of this lecture, attention will turn more closely to the resting electrical state itself, exploring how cells maintain calm stability and why this state is essential for all forms of signaling. For now, it is enough to rest with the understanding that every cell is alive with gentle electrical potential, sustained moment by moment in a state of quiet harmony. 3. The resting state and the quiet balance of electrical calm. Before any signal moves, before any message is sent, the body exists in a state of electrical stillness that is anything but empty. This condition, often referred to as the resting state, is the foundation upon which all cellular communication is built. It is a stable, carefully maintained balance that allows cells to remain responsive without being reactive, attentive without being active. In this quiet state, the body prepares itself continuously for the possibility of change. The resting electrical state of a cell is defined by a difference in electrical charge between its interior and the surrounding environment. This difference is subtle, measured in millivolts, yet it carries profound significance. Inside the cell, the electrical charge is slightly negative compared to the outside. This imbalance does not fluctuate wildly. It is held steady through constant regulation, forming a dependable baseline that allows the cell to function predictably. This resting potential emerges from the combined influence of ion distribution and membrane permeability. Potassium ions are especially important in this process. They are more concentrated inside the cell than outside, and because the membrane is more permeable to potassium than to many other ions, potassium tends to drift outward. As it does, it leaves behind negatively charged molecules that cannot cross the membrane. The result is a gentle accumulation of negative charge within the cell. At the same time, sodium ions are more concentrated outside the cell. Although there is a natural tendency for sodium to move inward, the membrane restricts this movement. Specialized pumps actively move sodium back out whenever it enters, preserving the gradient. This coordinated activity maintains the resting state, not as a fixed condition, but as a dynamic equilibrium sustained through continuous effort. It is important to recognize that rest, in biological terms, does not mean inactivity. The resting membrane potential requires ongoing energy and regulation. Ion pumps operate steadily, channels open and close subtly, and the internal environment of the cell is constantly monitored. This activity is quiet and efficient, designed to maintain readiness rather than produce action. In neurons, the resting state is particularly crucial. These cells are capable of rapid electrical signaling, but only because they spend most of their time at rest. The contrast between rest and activity gives signals their meaning. Without a stable baseline, changes would blur together, and information would be lost. The resting state provides clarity by defining what is normal, allowing deviations to stand out. This principle extends beyond the nervous system. Muscle cells rely on a stable, resting potential to ensure that contractions occur only when appropriate. Cardiac cells maintain a resting state that supports rhythmic electrical cycles without descending into chaos. Even cells not typically associated with signaling depend on electrical stability to regulate transport, shape, and metabolism. The resting state also protects cells from exhaustion. Constant electrical activity would be energetically costly and potentially damaging. By maintaining calm most of the time, cells conserve energy and reduce wear on their molecular machinery. Activity is reserved for moments when it is needed, emerging briefly and then subsiding back into balance. Another important feature of the resting state is its adaptability. While the general pattern of a negative interior is consistent, the exact value of the resting potential can vary between cell types and even within the same cell over time. These variations reflect differences in function, environment, and physiological state. The resting state is not rigid, it is responsive in its own quiet way. Temperature, ion availability, and metabolic conditions all influence the resting potential. When the body is well rested and nourished, electrical balance is easier to maintain. During illness or stress, subtle shifts may occur as cells adapt to new demands. Even then, the body works to preserve stability, adjusting gradually rather than abruptly. The resting electrical state also plays a role in development and healing. During early growth, changes in membrane potential can influence how cells specialize and organize themselves into tissues. In damaged tissue, electrical gradients help guide repair, encouraging cells to migrate and differentiate appropriately. These processes unfold slowly, guided by gentle electrical cues rather than dramatic signals. From a broader perspective, the resting state reflects a fundamental theme in biology. Balance supports complexity. By maintaining stable internal conditions, cells create the space for intricate interactions to occur without interference. Electrical calm allows chemical reactions, structural changes, and communication networks to operate in harmony. This calm is mirrored in the experience of rest at the level of the whole organism. During sleep or quiet wakefulness, overall electrical activity in the nervous system shifts towards slower rhythms. While individual cells maintain their resting potentials, patterns of activity become more synchronized and subdued. It is worth noting that the resting state is not an absence of information, but a form of information itself. When this potential changes, even slightly, it conveys meaning. In this way, the resting state is part of the language of the body, a silent phrase that says, "All is well." As you continue to rest and listen, your own cells are maintaining this quiet electrical balance. Nothing needs to happen for this balance to be valuable. In the parts that follow, attention will shift from this calm baseline to the gentle transitions that occur when cells move from rest into activity. These transitions will be explored slowly, emphasizing continuity rather than disruption. For now, it is enough to settle into the understanding that rest itself is an active, sustaining force, quietly upheld by the steady electrical nature of living cells. 4. Ions and the gentle carriers of electrical charge. Within the quiet electrical balance of the body, these ions are simple particles, atoms that have gained or lost an electron, yet their behavior shapes every electrical event in living tissue. They do not rush or collide dramatically. Instead, they drift, respond, and settle according to gradients that are carefully maintained by the cell. In this way, ions become the quiet carriers of the body's electrical language. An ion differs from a neutral atom because of its charge. When an atom loses an electron, it becomes positively charged. When it gains one, it becomes negatively charged. In the body, the most important ions involved in electrical activity are sodium, potassium, calcium, and chloride. Each of these ions plays a specific role, not because of complexity, but because of consistency. Their charges, sizes, and concentrations remain reliably predictable, allowing cells to build stable systems around them. Sodium ions are abundant in the fluid outside cells. They carry a positive charge and are naturally drawn toward the negatively charged interior of the cell. Potassium ions, also positively charged, are more concentrated inside cells. Calcium ions are present in much smaller quantities, but carry a strong positive charge that gives them significant influence. Chloride ions, which are negatively charged, often balance positive charges and contribute to electrical stability. The movement of these ions is guided by two main forces. One is the electrical gradient, which draws opposite charges together and pushes like charges apart. The other is the concentration gradient, which reflects the tendency of particles to spread out evenly. Ions move in response to both forces at once, seeking balance rather than motion for its own sake. When a membrane restricts their movement, electrical potential builds quietly. The cell membrane plays a central role in shaping this movement. Its lipid structure resists the passage of charged particles, meaning ions cannot simply drift across it freely. Instead, their movement depends on specific pathways. Ion channels embedded in the membrane provide these pathways, opening and closing in response to subtle conditions. Some channels remain open much of the time, allowing a slow and steady exchange. Others open only briefly, permitting controlled bursts of movement. This selectivity is essential. If all ions could move freely at all times, electrical differences would disappear, and with them, the capacity for signaling. By limiting ion flow, the membrane allows cells to store electrical potential, releasing it only when appropriate. In this sense, ions are both constrained and empowered by the structures around them. Ion pumps add another layer of control. These protein complexes actively move ions against their natural gradients, using energy to maintain separation. The sodium-potassium pump is a familiar example, steadily pushing sodium out of the cell and pulling potassium in. This activity may seem repetitive, but it is foundational. Without it, gradients would slowly dissolve, and electrical calm would fade. Calcium ions deserve particular attention because of their strong influence despite their low concentration. A small influx of calcium can have significant effects, triggering chemical reactions, muscle contraction, or neurotransmitter release. Because of this potency, cells keep calcium levels tightly regulated, storing it in specialized compartments and allowing it into the cytoplasm only briefly. Calcium's role illustrates how ions can act as both electrical and chemical messengers. Chloride ions contribute to balance by offsetting positive charges. Their movement often stabilizes membrane potential, preventing excessive excitation. In many neurons, chloride flow supports inhibitory signaling, gently reducing activity rather than amplifying it. This calming influence highlights that electrical signaling is not solely about activation, but about restraint and modulation. The body's fluids provide a supportive medium for ion movement. Water surrounds ions, allowing them to remain dissolved and mobile. This hydration softens their interactions, ensuring that electrical changes unfold smoothly rather than abruptly. The result is a system that favors gradual transitions and controlled responses. Ion distribution is not static. Cells continuously adjust their internal concentrations in response to changing conditions. During sustained activity, ion gradients may shift slightly, prompting the cell to restore balance through increased pump activity. During rest, gradients are preserved with minimal effort. These adjustments occur quietly, without disrupting overall stability. Across tissues, coordinated ion movement creates larger electrical patterns. In the heart, waves of ion flow produce rhythmic contractions. In muscles, synchronized ion shifts lead to smooth movement. In the brain, subtle changes in ion distribution underlie thought, perception, and rest. Yet at every level, the same principles apply. Ions move in response to gradients, guided by membranes and proteins that favor order over chaos. It is important to note that ions do not act with intention or awareness. They follow physical laws, responding predictably to forces and constraints. The elegance of biological electrical signaling arises not from the ions themselves, but from the way living systems harness their natural tendencies. By shaping environments and boundaries, cells transform simple movements into meaningful communication. This transformation is remarkably energy efficient. Because ions tend naturally toward balance, cells need only apply energy to maintain separation, not to force movement at every step. Once gradients are established, ions do much of the work themselves, drifting along paths that have been carefully prepared. This efficiency supports the body's ability to function continuously without strain. As you rest, ions are moving within you at this very moment. Sodium and potassium drift across membranes. Calcium waits in reserve. Chloride balances charges quietly. None of this requires attention or effort. It unfolds steadily, sustaining the electrical conditions that make awareness and rest possible. In the next part of this lecture, attention will turn more closely to the cell membrane itself, exploring how its structure allows such precise control over ion movement. For now, it is enough to remain with the image of ions as gentle carriers, drifting patiently through a landscape shaped for balance, quietly supporting the living electrical harmony of the body. 5. The cell membrane as a patient and selective gate. Every electrical event in the body depends upon a structure so thin it cannot be seen with the unaided eye, yet so reliable that life would unravel without it. The cell membrane is this structure, a flexible boundary that surrounds every cell, quietly defining where the cell ends and the surrounding world begins. Far from being a simple wall, the membrane is an active, discerning presence, shaping electrical activity through patience, selectivity, and constant regulation. At its core, the cell membrane is composed of a double layer of lipids, arranged with remarkable consistency. These lipid molecules have a dual nature. One part is comfortable in water, while the other avoids it. As a result, when placed in an aqueous environment, they naturally arrange themselves into a bilayer, with water-friendly ends facing outward and water-repelling ends tucked safely inside. This simple physical property gives rise to a stable, self-sealing boundary that can bend, flex, and repair itself without losing integrity. This lipid bilayer forms the foundation of the membrane's electrical role. Because charged particles do not pass easily through the fatty interior of the bilayer, ions are effectively separated into inside and outside populations. This separation allows electrical differences to exist and persist. Without it, ions would diffuse freely, and the electrical calm described in earlier parts would dissolve into uniformity. Embedded within this lipid landscape are proteins, each with a specific role. Others act as anchors, connecting the membrane to internal structures. Most relevant to electrical signaling are the proteins that form channels and transporters. These proteins create controlled pathways through which ions may pass, one type at a time, under carefully defined conditions. Ion channels are not simple holes. They are highly selective structures shaped to recognize specific ions based on size and charge. A sodium channel, for instance, welcomes sodium ions while excluding potassium, even though the two are similar. This selectivity allows the cell to regulate its electrical state with precision. Some channels are always open, allowing a slow, continuous exchange that supports the resting electrical state. These so-called leak channels do not produce dramatic changes. Instead, they contribute to the steady background movement of ions that defines electrical calm. Other channels remain closed until prompted, opening only in response to particular signals such as changes in voltage, the binding of a chemical messenger, or mechanical deformation of the membrane. The opening and closing of channels is not abrupt or violent. It is a subtle shift in protein shape, guided by forces already present in the cell's environment. When a channel opens, ions flow according to existing gradients, drifting rather than being pushed. When it closes, the flow simply stops, and balance is restored. This gentle gating ensures that electrical changes are smooth and reversible. Transporter proteins add another dimension to membrane selectivity. Unlike channels, which allow ions to move down their gradients, transporters can move substances against those gradients. This activity requires energy, and it is here that the cell invests effort to maintain separation and readiness. By selectively moving ions in this way, transporters preserve the conditions that make signaling possible. The membrane's role as a gate extends beyond ions alone. It also regulates the movement of nutrients, waste products, and signaling molecules. Each passage is controlled, ensuring that the internal environment remains stable even as the external environment fluctuates. Electrical balance depends on this broader stability. A membrane that allowed uncontrolled exchange would compromise not only electrical signaling but all aspects of cellular life. Importantly, the membrane is not uniform across its entire surface. Different regions may contain different concentrations of channels and receptors, reflecting the specialized functions of the cell. In neurons, for example, certain areas of the membrane are especially rich in voltage-sensitive channels, preparing them for rapid electrical activity. Other regions emphasize stability and integration, reinforcing the resting state. Despite this specialization, the membrane maintains continuity. Electrical changes in one region influence neighboring areas, spreading gently along the surface. This continuity allows signals to travel without gaps, guided by the membrane's structure and composition. The membrane thus serves not only as a boundary, but as a medium for electrical change. The flexibility of the membrane also contributes to its role. It can stretch and compress slightly without tearing, accommodating changes in cell shape and volume. This flexibility ensures that electrical properties remain stable even as cells move, divide, or interact with their surroundings. The membrane adapts quietly, preserving function through change. From a broader perspective, the membrane embodies a central principle of living systems: control without rigidity. It does not resist all change, nor does it allow everything to pass. Instead, it balances openness with restraint, permitting movement when appropriate and maintaining separation when necessary. Electrical signaling depends on this balance, unfolding within boundaries that are firm yet responsive. As you rest, your cells are enclosed by billions of these membranes, each one quietly maintaining electrical readiness. Ions wait near channels, gradients persist, and the internal environment remains distinct yet connected. None of this requires awareness. It is sustained automatically, moment by moment, by structures shaped through evolution to favor stability. In the parts ahead, attention will move from the membrane itself to the gentle beginnings of electrical signals, exploring how changes in membrane behavior give rise to activity. For now, it is enough to recognize the membrane as a patient gatekeeper, holding the line between inside and outside, and in doing so, preserving the calm electrical foundation upon which all signaling depends. 6. How a nerve signal gently begins. Within the calm electrical landscape of the body, nerve signals do not erupt suddenly or without cause. They arise gradually, shaped by quiet conditions that build toward change. A nerve signal begins not as a dramatic event, but as a subtle shift, a small departure from rest that reflects the cell's careful attention to its surroundings. This beginning is measured, predictable, and deeply rooted in the stability that precedes it. A neuron at rest holds its electrical balance patiently. The interior remains slightly negative, the membrane selective, the ions arranged according to long-maintained gradients. This state is not fragile. Small disturbances occur constantly, and most of them fade without consequence. A faint touch, a passing chemical signal, a minor fluctuation in temperature may cause ions to move briefly across the membrane. These movements produce tiny electrical changes that ripple locally and then dissolve back into calm. These small changes are known as graded responses. Importantly, they do not automatically lead to a full nerve signal. The neuron integrates many such influences, adding and subtracting their effects over time. Only when these changes accumulate sufficiently does the neuron move toward activity. This accumulation occurs primarily at a specialized region of the neuron, where the cell body transitions into the long projection known as the axon. This region is especially sensitive to electrical change. It contains a high concentration of voltage-sensitive ion channels, making it more responsive than other parts of the membrane. Here, the neuron quietly evaluates whether conditions warrant a response. The idea of a threshold is central to this evaluation. Threshold does not represent a rigid line, but a functional point at which the balance tips. Below threshold, electrical changes remain local and reversible. At threshold, the membrane's behavior shifts. Voltage-sensitive channels begin to open in a coordinated way, allowing ions to move more freely. This opening is not forced. It follows naturally from the conditions that have developed. When threshold is reached, sodium ions play a leading role, because they are abundant outside the cell and drawn inward by both electrical and concentration gradients. They flow into the neuron once channels open. This influx reduces the negative charge inside the cell, a process known as depolarization. As depolarization progresses, it encourages additional sodium channels to open, reinforcing the change. This process might sound like escalation, but it remains tightly controlled. The channels respond to specific voltage conditions and close again once those conditions change. As sodium enters, the membrane potential shifts rapidly but predictably. The neuron transitions from rest into a brief state of electrical activity, generating what is known as an action potential. The beginning of an action potential is not a loss of control. Once initiated, the process follows a consistent pattern, unfolding smoothly and then resolving. The neuron does not choose whether to respond in the moment. It responds because conditions have quietly aligned. Equally important is what does not trigger a nerve signal. Countless minor fluctuations never reach threshold. They fade, absorbed into the background of electrical calm. This selectivity protects the nervous system from overload, ensuring that only meaningful patterns of input result in activity. The body values restraint as much as responsiveness. After the initial depolarization, additional mechanisms ensure that the signal remains brief. At the same time, potassium channels open, allowing potassium ions to leave the cell. This outward movement restores the negative interior, guiding the membrane back toward its resting state. The neuron resets itself, ready to respond again if needed. This cycle of readiness, response, and recovery occurs rapidly, yet it is built upon slow, steady maintenance. Without the resting state and the careful arrangement of ions, none of this would be possible. The nerve signal's beginning depends entirely on what came before it: stability, patience, and balance. From a broader perspective, the gentle initiation of nerve signals reflects a design that favors clarity over speed. Signals begin only when they should, shaped by the combined influence of many inputs. This integration allows the nervous system to represent complex information, not as isolated flashes, but as patterns that emerge from context. As you listen and rest, neurons throughout your body are engaged in this quiet evaluation. Most remain at rest, holding their electrical balance without disturbance. A few respond, perhaps to posture, breathing, or subtle sensory input. Each response begins the same way, with a gentle shift that reaches threshold and unfolds into activity before settling back into calm. In the next part of this lecture, attention will turn to how these signals travel once they have begun, moving along the neuron as a coordinated wave rather than a scattered event. For now, it is enough to rest with the understanding that every nerve signal begins patiently, emerging from stillness only when conditions quietly invite it to do so. 7. The action potential as a traveling wave. Once a nerve signal has gently begun, it does not remain fixed at its point of origin. Instead, it moves, progressing along the length of the neuron in a smooth and orderly manner. This movement is often described as the propagation of an action potential, but it is helpful to think of it less as something being sent and more as something unfolding. The signal travels not because it is pushed forward, but because each small region of the membrane responds in turn to changes in its immediate neighbor. At the moment an action potential begins, a small section of the neuron's membrane undergoes a rapid change in electrical state. Sodium ions enter, the interior becomes briefly positive, and the local balance shifts. This change does not remain isolated. Electrical differences influence nearby regions of the membrane, slightly altering their voltage. These neighboring regions, sensing the change, respond if the shift is sufficient, opening their own voltage-sensitive channels. In this way, the signal moves forward as a coordinated sequence of local events. The wave-like nature of this movement is essential. The action potential does not leap from one end of the neuron to the other, nor does it drain away as it travels. Each segment of the membrane regenerates the signal anew, guided by the same principles that initiated it. Because the underlying ion gradients are maintained along the entire length of the neuron, the signal retains its strength from beginning to end. This regenerative quality distinguishes nerve signals from simple electrical currents traveling through a wire. In a wire, electrical energy diminishes with distance unless reinforced. In a neuron, the signal is continuously refreshed. Each opening of sodium channels restores the full electrical change, ensuring reliable transmission regardless of length. This is why neurons can extend great distances within the body, from the spinal cord to the toes, without losing the clarity of their messages. As the action potential moves forward, it leaves behind a region of membrane that has just completed its cycle of activity. In this region, sodium channels are temporarily inactive, and potassium channels are restoring the resting state. This brief period, known as refractoriness, prevents the signal from reversing direction. The wave moves forward not because it is forced, but because backward movement is momentarily impossible. This one-way progression contributes to the orderly flow of information. The speed at which an action potential travels varies between neurons. Some signals move slowly, while others travel with remarkable efficiency. This variation is not random. It reflects differences in neuron diameter, membrane properties, and structural adaptations. Larger axons allow ions to spread more easily along the interior, supporting faster propagation. Structural refinements further enhance this efficiency, though the underlying wave-like process remains the same. Despite differences in speed, the fundamental pattern of propagation is consistent. The membrane ahead of the wave is at rest, ready but inactive. The membrane within the wave is briefly active, allowing ion movement. The membrane behind the wave is recovering, restoring balance. These three states coexist moment by moment, forming a moving pattern that carries information without disrupting overall stability. It is important to note that the action potential is brief. At any given point along the neuron, the electrical change lasts only a fraction of a second. Once it has passed, the membrane returns to its resting condition. This transience allows neurons to send repeated signals over time without fatigue. Provided their metabolic needs are met, activity is woven into rest, not layered on top of it. The all-or-nothing nature of the action potential contributes to its reliability. Once threshold is reached, the signal unfolds in a consistent way. Stronger stimuli do not produce larger action potentials. Instead, they may produce signals more frequently or recruit additional neurons. This consistency ensures that the traveling wave remains uniform, easily recognized by downstream cells. As the signal travels, it remains insulated from interference. The membrane structure and the localized nature of ion movement prevent electrical noise from distorting the message. Each neuron conducts its own wave independently, even when surrounded by countless others doing the same. The nervous system thus supports parallel communication on an immense scale, all unfolding quietly and efficiently. From the perspective of the whole organism, this traveling wave enables coordination across distance. Sensory information from the skin can reach the brain. Commands from the brain can reach muscles. Reflexes can occur rapidly, without conscious involvement. All of this depends on the reliable movement of action potentials along neurons, guided by the same calm principles repeated endlessly. As you rest, these waves continue to travel within you. Some carry information related to posture or breathing. Others maintain internal rhythms. Many neurons remain silent, holding their resting state without change. Activity and stillness coexist, balanced by design. In the next part of this lecture, attention will turn to the structures that further refine this traveling process, allowing signals to move with even greater efficiency. For now, it is enough to rest with the image of the action potential as a gentle wave, moving steadily along a prepared path, carrying information without urgency and leaving calm in its wake. 8. Myelin and the quiet efficiency of insulation. As electrical signals travel along neurons, the body employs additional structures to make this movement more efficient, reliable, and calm. Among the most important of these structures is myelin, a substance that wraps around portions of certain neurons, forming an insulating layer. Myelin does not create electrical signals, nor does it decide when they begin. Instead, it shapes how they move, refining the traveling wave into something smoother and more economical. Myelin is produced by specialized supporting cells in the nervous system. In the brain and spinal cord, these are called oligodendrocytes, while in peripheral nerves they are known as Schwann cells. Though their names differ, their role is essentially the same. This wrapping is precise and deliberate, leaving certain regions exposed while covering others. The material that makes up myelin is rich in lipids, similar in some ways to the lipid bilayer of the cell membrane, but arranged in multiple layers. Because lipids resist the movement of charged particles, myelin acts as an insulator. It reduces the leakage of ions across the axon membrane, preserving electrical differences and preventing signal loss. In doing so, it allows the action potential to travel farther with less effort. Importantly, myelin does not cover the axon continuously from end to end. Instead, it is arranged in segments, with small gaps between them, known as nodes. At these nodes, the axon membrane is exposed to the surrounding fluid and densely packed with ion channels. These regions become focal points for electrical activity, where the action potential is actively regenerated. As a result of this arrangement, the traveling wave of electrical activity appears to move in a distinctive way. Rather than progressing smoothly along every inch of the axon, the signal seems to jump from node to node. This process is often described as saltatory conduction, a term that reflects its leaping quality. Yet, despite the name, nothing about this movement is abrupt or uncontrolled. The signal remains continuous in effect, guided by the underlying structure of the axon and its insulation. This mode of conduction offers several advantages. By limiting active ion exchange to the nodes, the neuron reduces the amount of energy required to restore ion gradients after each signal. Fewer ions cross the membrane overall, and fewer pumps are needed to reset the resting state. This efficiency allows neurons to transmit signals rapidly without exhausting their resources. Speed is another benefit. Because the insulated regions prevent electrical charge from dissipating, changes in voltage spread quickly along the interior of the axon. The next node reaches threshold sooner, and the signal continues with minimal delay. In some neurons, this allows signals to travel at remarkable speeds, coordinating movement and sensation with precision. Despite these advantages, myelin does not introduce complexity for its own sake. It builds upon the same principles already discussed: separation, selective permeability, and gradient maintenance. Myelin simply extends these principles over larger distances, ensuring that electrical calm and readiness are preserved even as signals travel far from their point of origin. Not all neurons are myelinated. Some axons lack this insulation and conduct signals more slowly. This is not a flaw, but a reflection of functional diversity. In certain contexts, slower signaling is sufficient or even preferable. The nervous system balances speed and simplicity, applying myelin where it offers clear benefits and leaving other pathways uninsulated. The presence of myelin also contributes to the stability of neural signaling. By reducing electrical noise and preventing unintended ion movement, Myelin helps ensure that signals remain distinct and well-timed. This clarity supports complex patterns of activity in the brain, where millions of neurons operate in close proximity. Myelin's importance becomes especially apparent when it is disrupted. Conditions that damage myelin interfere with signal conduction, slowing or distorting communication. This underscores the role of insulation not as an accessory, but as an integral part of electrical signaling. The smooth flow of information depends not only on the signal itself, but on the environment through which it moves. From a developmental perspective, myelination unfolds gradually. In humans, many neurons are not fully myelinated at birth. Insulation increases throughout childhood and adolescence, paralleling the refinement of motor skills, sensory processing, and cognitive function. This gradual progression reflects the nervous system's adaptive nature, adding efficiency as demands increase. Even in adulthood, myelin remains dynamic. Supporting cells can adjust myelin thickness and distribution in response to activity, subtly tuning conduction properties. This adaptability allows the nervous system to optimize performance over time, reinforcing frequently used pathways while maintaining overall balance. As you rest, countless myelinated axons within you are quietly maintaining their structure. The insulation holds, the nodes stand ready, and electrical signals move efficiently when needed. Much of this activity remains invisible, unfolding beneath awareness without effort. In the next part of this lecture, attention will shift to what happens when a traveling signal reaches the end of a neuron and encounters another cell. For now, it is enough to remain with the image of myelin as quiet insulation, wrapping signals in efficiency, allowing them to travel smoothly through a system designed for calm coordination rather than haste. 9. From one cell to the next, and the quiet space of the synapse. When an electrical signal has traveled the length of a neuron, its journey does not simply continue into the next cell in a continuous stream. Instead, it arrives at a boundary, a small but meaningful pause in the flow of information. This pause occurs at a structure known as the synapse, a narrow space that separates one cell from another. Within this tiny gap, electrical signaling gives way to a different form of communication, one that is slower, more flexible, and deeply refined. The synapse is not an empty void. It is an organized and carefully maintained region where communication unfolds with precision. At the end of the neuron that carries the signal, the axon widens slightly into a terminal. These molecules wait quietly, held in reserve, ready to be released only when the right conditions arise. As the action potential reaches the axon terminal, it does not leap across the synaptic gap. Instead, it triggers a change within the terminal itself. The arrival of the electrical wave alters the membrane potential, opening channels that allow calcium ions to enter. Calcium, though present in small amounts, carries significant influence. Its entry into the terminal acts as a signal that activity has arrived. This influx of calcium sets in motion a series of calm and orderly events. Vesicles containing neurotransmitters move toward the membrane of the terminal and merge with it. Through this merging, neurotransmitters are released into the synaptic space. The release is not explosive. It is measured, releasing only a small quantity of molecules, enough to convey information without excess. Once in the synaptic space, neurotransmitters diffuse across the narrow gap. This space is only a few nanometers wide, yet it plays a crucial role in shaping communication. The delay introduced by diffusion allows for modulation and control. It ensures that signals are not forced forward blindly, but are instead evaluated by the receiving cell. On the far side of the synapse lies the membrane of the receiving cell, often another neuron, but sometimes a muscle or gland cell. Embedded in this membrane are specialized receptor proteins, each shaped to recognize specific neurotransmitters. When a neurotransmitter binds to its receptor, it causes a subtle change in the receptor's shape, triggering a response within the receiving cell. This response often involves the opening or closing of ion channels. In this way, Chemical signaling at the synapse is translated back into electrical change. Depending on the type of neurotransmitter and receptor involved, the effect may be excitatory. The balance between these influences determines how the receiving cell responds. The synapse introduces flexibility into neural communication. Unlike action potentials, which are uniform and all or nothing, synaptic signals can vary in strength. The amount of neurotransmitter released, the sensitivity of receptors, and the timing of release all contribute to the outcome. This variability allows the nervous system to fine-tune its responses, adapting to context rather than reacting mechanically. Another important feature of synaptic communication is directionality. Signals move from the sending cell to the receiving cell, guided by the structure of the synapse. This directionality supports organized information flow, ensuring that messages travel along meaningful pathways rather than spreading indiscriminately. After neurotransmitters have conveyed their message, they do not linger indefinitely. The synapse is cleared through several mechanisms. Some neurotransmitters are taken back into the sending cell for reuse. Others are broken down by enzymes within the synaptic space. These processes restore the synapse to readiness, preventing continuous stimulation and preserving balance. The presence of the synapse allows the nervous system to integrate information from many sources. A single neuron may receive input from thousands of synapses, each contributing a small influence. These influences accumulate and interact, shaping the cell's overall electrical state. In this way, the synapse serves as a site of convergence, where diverse signals are weighed and combined. Synapses are also dynamic structures. Their strength can change over time, reflecting patterns of activity. Frequent use can enhance synaptic responsiveness, while inactivity may lead to weakening. This adaptability underlies learning and memory, allowing experience to shape neural pathways without altering the fundamental electrical principles involved. Despite their complexity, synapses operate quietly and efficiently. The chemical exchanges they host are localized and transient, unfolding without disruption to surrounding tissue. Each synapse functions as a discrete conversational space, allowing cells to communicate privately within the broader network. As you rest, countless synapses within your nervous system are active at low levels, maintaining tone and readiness. Others remain silent, their vesicles waiting patiently. This balance between activity and rest supports calm awareness and the ability to respond when needed. In the next part of this lecture, attention will turn to the way electrical and chemical signaling work together as a unified system rather than separate processes. For now, it is enough to remain with the image of the synapse as a quiet meeting place where signals pause, transform, and continue, guided by restraint, precision, and gentle coordination. 10. Electrical and chemical signaling as one continuous conversation. Within the body, electrical and chemical signaling are often described as separate processes. Yet in living systems, they are deeply intertwined, forming a single, continuous conversation that unfolds without interruption. Electrical changes give rise to chemical release. Chemical messages shape electrical responses, and together they create a seamless flow of information. Rather than alternating sharply between two modes, the body blends them gently, allowing communication to remain flexible, precise, and calm. Electrical signaling excels at speed and direction. An action potential moves swiftly along a neuron, guided by membrane properties and ion gradients. Chemical signaling, by contrast, introduces nuance and adaptability. At synapses, neurotransmitters can vary in type, quantity, and effect, allowing signals to be shaped rather than merely transmitted. The nervous system relies on both qualities, speed and subtlety. When an electrical signal reaches the end of a neuron, it does not stop or dissipate. Instead, it transforms. The arrival of the action potential alters the electrical state of the axon terminal, opening calcium channels and triggering neurotransmitter release. This chemical step is not a detour, but an extension of the same process, allowing the signal to cross a physical gap while gaining flexibility. On the receiving side, chemical messages once again become electrical. Neurotransmitters bind to receptors, ion channels respond, and membrane potentials shift. Some shifts are small and temporary, reinforcing rest or gently encouraging activity. Others accumulate, contributing to the possibility of a new action potential. In this way, chemical signals do not replace electrical ones. They modulate them, shaping how and when electrical activity resumes. This interplay allows the nervous system to integrate vast amounts of information. Electrical signals provide a reliable backbone, ensuring that messages arrive intact and on time. Chemical signals adjust tone and context, determining whether a message should be amplified, dampened, or ignored. Together, they support complex behavior without sacrificing stability. The blending of electrical and chemical signaling is not limited to neurons alone. In muscle tissue, electrical changes at the cell membrane trigger the release of calcium within the cell, leading to contraction. In glandular tissue, electrical activity influences chemical secretion, coordinating hormonal messages that travel through the bloodstream. Across systems, the same pattern repeats. Electrical change initiates chemical response, which in turn influences electrical state elsewhere. This pattern underscores an important principle. The body does not rely on a single form of communication. Instead, it uses layered signaling, allowing different modes to complement one another. Electrical signals provide immediacy, while chemical signals provide persistence. Electrical changes are brief and localized. Chemical signals can linger and spread. The combination allows the body to respond quickly while also maintaining longer-term regulation. The chemical component of signaling also introduces the possibility of diversity. There are many types of neurotransmitters and receptors, each with distinct effects. Some neurotransmitters encourage activity, others promote calm. This diversity allows the nervous system to tailor responses with remarkable precision, using the same electrical framework to support many outcomes. Yet despite this complexity, the system remains orderly. Chemical signaling does not overwhelm electrical stability. Neurotransmitters are released in controlled amounts and cleared efficiently. Receptors respond transiently and then reset. The underlying electrical gradients are preserved, ensuring that cells remain ready rather than depleted. Balance is maintained not by limiting communication, but by regulating it. From the perspective of the whole organism, this integrated signaling supports both responsiveness and rest. During active moments, electrical and chemical signals coordinate movement, perception, and decision-making. During rest and sleep, signaling shifts towards slower rhythms and inhibitory influences, promoting recovery and consolidation. The same systems are at work in both states, adjusted gently rather than switched off. This continuity is especially evident in the brain, where billions of neurons communicate constantly. Some pathways quiet, others synchronize, and still others engage in maintenance and integration. Chemical modulators adjust overall tone, while electrical rhythms reflect collective activity. Together, they sustain a state of rest that is active in its own way. The integration of electrical and chemical signaling also supports resilience. Because communication unfolds across multiple layers, disruption in one area can often be compensated by adjustments elsewhere. If electrical conduction slows, chemical modulation may adjust sensitivity. If chemical signaling wanes, electrical thresholds may shift. This adaptability helps preserve function across changing conditions. As you rest and listen, this conversation continues within you. Electrical waves travel, chemical messages are released and cleared, and cells respond with restraint. None of this requires attention. It is guided by structures and processes refined to operate quietly and reliably. In the next part of this lecture, attention will turn to the specific roles of different neurotransmitters and how they influence the balance between activity and calm. For now, it is enough to remain with the understanding that electrical and chemical signaling are not separate stories, but two voices in a single, ongoing dialogue, one that sustains awareness, movement, and rest through gentle coordination rather than force. 11. Neurotransmitters and their gentle influence on balance. Within the quiet space of the synapse, neurotransmitters act as subtle guides rather than commanding forces. They do not shout instructions or impose outcomes. Instead, they influence probability, gently shaping whether a receiving cell is more likely to remain at rest or move toward activity. In this way, neurotransmitters contribute to balance rather than disruption, fine-tuning communication across the nervous system with remarkable restraint. Neurotransmitters are chemical messengers synthesized within neurons and stored in small vesicles near the synapse. Each type has a characteristic structure that allows it to interact with specific receptors. When released, neurotransmitters diffuse across the synaptic space and bind to these receptors, initiating changes that alter the electrical state of the receiving cell. Yet this interaction is temporary. Neurotransmitters bind, act, and then are removed or broken down, ensuring that their influence is brief and controlled. Some neurotransmitters are primarily excitatory. They increase the likelihood that the receiving neuron will move toward threshold, making electrical activity more probable. Glutamate is the most common example of this type. It is widely distributed throughout the nervous system and plays a central role in sensory processing, movement, and learning. When glutamate binds to its receptors, ion channels open in a way that allows positively charged ions to enter the cell, gently reducing the negative interior and nudging the membrane potential upward. Other neurotransmitters are primarily inhibitory. They do not silence neurons entirely, but they reinforce the resting state, making activity less likely. Gamma-aminobutyric acid, often called GABA, is a key inhibitory neurotransmitter. When GABA binds to its receptors, it typically allows chloride ions to enter the cell or potassium ions to leave, both of which support a more negative membrane potential. This influence promotes calm and stability, counterbalancing excitation. The nervous system depends on a careful balance between excitation and inhibition. Too much excitation would lead to constant activity, overwhelming cells, and depleting energy. Too much inhibition would suppress responsiveness, limiting the ability to react to the environment. Neurotransmitters ensure that neither extreme dominates. They work together, creating a dynamic equilibrium that supports both readiness and restraint. Some neurotransmitters act less directly on membrane potential and instead modulate how neurons respond to other signals. Dopamine, serotonin, and norepinephrine fall into this category. These modulatory neurotransmitters do not typically produce rapid electrical changes on their own. Instead, they alter the sensitivity of receptors, the strength of synapses, or the internal state of the neuron. Their influence unfolds slowly, shaping overall tone rather than moment-to-moment signaling. Dopamine is often associated with motivation and reward, but at the cellular level, it functions as a modulator of signaling pathways. It can enhance or reduce the impact of excitatory and inhibitory inputs, adjusting how neurons respond based on context and experience. Serotonin contributes to mood regulation and sleep-wake cycles by subtly shifting neural activity toward calm or alertness depending on circumstances. Norepinephrine influences attention and arousal, gently tuning responsiveness without forcing action. These modulatory neurotransmitters highlight an important feature of chemical signaling. Some are about setting conditions, preparing networks to respond differently over time. This slower influence supports adaptation, learning. Neurotransmitters also vary in how long they persist. Others linger longer, extending their influence. Enzymes and reuptake mechanisms ensure that even longer-lasting neurotransmitters are eventually removed, restoring the synapse to baseline. This clearance is essential. Without it, signals would blur together, and balance would be lost. The diversity of neurotransmitters allows the nervous system to encode rich information using a limited electrical framework. Action potentials are uniform, but neurotransmitters provide variety. Different combinations of chemical signals can convey meaning beyond simple presence or absence of activity. This chemical nuance transforms electrical pulses into complex communication. Importantly, neurotransmitters do not act in isolation. At any given synapse, multiple types may be present, and receptors may respond to more than one messenger. The receiving cell integrates these influences, responding not to a single molecule, but to a pattern. This integration supports subtle decision-making at the cellular level, ensuring that responses reflect overall context rather than isolated input. From a metabolic perspective, neurotransmitter systems are efficient. Synthesis, release, and recycling are tightly regulated, conserving resources while maintaining readiness. Vesicles are refilled, receptors reset, and ion gradients restored, all without excess. This efficiency supports sustained function over a lifetime. As you rest, neurotransmitters within your nervous system are quietly maintaining balance. Inhibitory signals support relaxation, excitatory ones remain restrained, and modulatory influences adjust overall tone. Even in sleep, neurotransmitter activity continues, shifting patterns to support restoration and memory consolidation. In the next part of this lecture, attention will turn to how excitation and inhibition work together within networks of neurons, creating coordinated patterns rather than isolated responses. For now, it is enough to remain with the understanding that neurotransmitters are gentle influencers, shaping electrical activity not through force, but through balance, timing, and quiet modulation. 12. Excitation and inhibition, and the art of neural balance. Within the nervous system, activity is never simply about turning signals on or off. Instead, it is shaped by a continuous interplay between excitation and inhibition, two complementary influences that work together to maintain balance. This balance is not static. It shifts gently from moment to moment, allowing the body to remain responsive without becoming overwhelmed. Excitation refers to influences that make a neuron more likely to generate an electrical signal. These influences typically involve neurotransmitters that slightly reduce the negative charge inside the cell, bringing the membrane potential closer to threshold. Inhibition, by contrast, involves influences that reinforce the resting state, increasing the distance between the current membrane potential and the point at which a signal would begin. Neither influence acts alone, and neither is inherently dominant. At the level of a single neuron, excitation and inhibition arrive through many synapses. Each synapse contributes a small effect, either nudging the cell toward activity or encouraging it to remain still. These effects accumulate in time and space, combining into a net influence. The neuron does not respond to individual inputs in isolation. Instead, this integration is continuous. Even in moments of apparent rest, neurons receive a steady stream of excitatory and inhibitory input. The balance between them maintains the resting state, holding the membrane potential within a stable range. When excitation briefly outweighs inhibition, activity becomes more likely. When inhibition dominates, the cell remains quiet. Inhibitory influences play a particularly important role in shaping neural activity. By limiting when and where signals occur, inhibition prevents excessive firing and ensures that activity remains focused. It sharpens responses, allowing neurons to respond selectively to meaningful patterns while ignoring background noise. In this way, inhibition enhances clarity rather than suppressing function. Excitation, for its part, provides the capacity for change. Without excitatory input, neurons would remain locked in rest, unable to respond to the environment. Excitation introduces possibility, opening a window through which activity may emerge. Yet excitation alone would be chaotic. Only through its balance with inhibition does it become useful. This balance extends beyond individual neurons to entire networks. Groups of neurons often exhibit coordinated patterns of excitation and inhibition, creating rhythms that reflect different functional states. In waking consciousness, certain patterns dominate, supporting perception and movement. In sleep, other patterns emerge, emphasizing synchronization and rest. In each case, excitation and inhibition work together to shape the overall state. The timing of these influences is also crucial. Excitatory and inhibitory signals may arrive simultaneously or in sequence. A brief inhibitory input following excitation can limit the duration of activity, creating a precise signal. Alternatively, inhibition may precede excitation, setting conditions that make the cell more selective in its response. These temporal relationships add another layer of control, refining communication without adding complexity. The strength of synaptic influences can change over time, reflecting experience and adaptation. Frequently used excitatory synapses may become more effective, while unused ones weaken. Inhibitory synapses also adapt, adjusting their influence to maintain balance as networks change. This plasticity ensures that excitation does not gradually overpower inhibition, or vice versa. Balance is preserved through ongoing adjustment. From an energetic perspective, inhibition is efficient. By preventing unnecessary activity, it conserves resources and reduces metabolic demand. This efficiency supports long-term stability, allowing the nervous system to function reliably over decades. Excitation, though more energetically demanding, is deployed selectively, ensuring that energy is spent where it matters most. At the level of experience, this balance underlies the ability to focus, relax, and transition smoothly between states. Calm attention reflects a state in which excitation and inhibition are well matched. Anxiety or restlessness often involves shifts in this balance, with excitation temporarily outweighing inhibitory control. Sleep represents a coordinated adjustment, with inhibitory influences becoming more prominent and excitatory activity becoming more synchronized. As you rest and listen, your nervous system is maintaining this balance quietly. Excitatory signals remain present but restrained, ready to respond if needed. This poised state allows rest to unfold without vulnerability. Importantly, balance does not imply symmetry. At times, excitation dominates, enabling action and engagement. At other times, inhibition leads, supporting recovery and integration. The nervous system moves fluidly between these modes, guided by internal needs and external conditions. In the next part of this lecture, attention will turn to how electrical signaling extends beyond neurons, influencing muscles, organs, and other tissues. For now, it is enough to remain with the understanding that excitation and inhibition are not opposing forces locked in conflict, but partners in a shared task, shaping neural activity through cooperation, restraint, and quiet balance. 13. Electrical signals beyond the brain and into the body. Although the brain and spinal cord often receive the most attention when discussing electrical signaling, they are only part of a much broader landscape. Electrical activity extends far beyond the nervous system, quietly coordinating functions throughout the body. Muscles, glands, and organs all rely on electrical properties to carry out their roles, using principles that closely resemble those found in neurons, yet adapted to their specific needs. In muscle tissue, electrical signals provide the link between intention and movement. Whether a motion is deliberate, like lifting an arm, or automatic, like breathing, it begins with a change in electrical state. Muscle cells maintain a resting membrane potential much like neurons do. This resting state preserves readiness, allowing the cell to respond when a signal arrives. The signal itself often originates in a motor neuron, but the muscle cell must translate that message into physical action. When an electrical signal reaches a muscle cell, it alters the membrane potential, opening channels that allow ions to move. This electrical change spreads across the muscle cell's membrane and into its interior through specialized structures. Calcium ions are released within the cell, initiating interactions between proteins that cause the muscle fibers to shorten. The contraction is smooth and coordinated, guided by the precise timing of electrical and chemical events. Once the signal ends, calcium is actively returned to storage, and the muscle cell relaxes. The membrane potential returns to its resting state, restoring readiness without lingering tension. This cycle of excitation and relaxation repeats effortlessly, allowing muscles to respond repeatedly without fatigue when conditions are balanced. The heart provides another striking example of electrical signaling beyond the brain. Cardiac muscle cells generate and conduct electrical signals independently, forming a self-regulating network. Specialized cells within the heart spontaneously shift their membrane potential, producing rhythmic electrical impulses that spread through the heart muscle. These impulses coordinate contraction, ensuring that blood is pumped efficiently. Although the heart's electrical activity is influenced by the nervous system, it does not depend on conscious control. Instead, it reflects a built-in rhythm shaped by membrane properties and ion channels unique to cardiac cells. Electrical signals in the heart are slower and more prolonged than those in neurons, supporting steady, rhythmic contraction rather than rapid communication. Glandular tissues also rely on electrical changes to regulate secretion. Cells in glands such as the pancreas, adrenal glands, and salivary glands adjust their membrane potential in response to signals from nerves or circulating hormones. These electrical changes influence the movement of ions in water, facilitating the release of hormones or enzymes. Once again, electrical and chemical signaling work together, ensuring that release occurs at the right time and in the right amount. Even tissues not typically associated with signaling exhibit electrical properties. Epithelial cells lining organs and blood vessels maintain membrane potentials that regulate transport and barrier function. Electrical gradients guide the movement of nutrients, electrolytes, and fluids. These gradients are subtle and persistent, shaping function quietly rather than dramatically. The digestive system offers a particularly gentle example of electrical coordination. Smooth muscle cells in the gut generate slow, rhythmic electrical waves that regulate contractions known as peristalsis. These waves move food along the digestive tract without conscious involvement. Nerves modulate this activity, adjusting speed and strength based on context. But the underlying rhythm arises from the electrical properties of the muscle cells themselves. Electrical signaling also plays a role in sensory systems beyond conscious perception. Specialized receptor cells in the skin, inner ear, and eyes convert physical stimuli into electrical changes. In the inner ear, for example, movement of fluid bends tiny structures that open ion channels, creating electrical signals that convey information about balance and sound. These signals are refined through layers of processing before reaching awareness, but their origin remains electrical. Importantly, electrical signaling outside the brain tends to emphasize stability and rhythm over rapid change. While neurons excel at transmitting brief, discrete signals, other tissues favor slower, sustained electrical patterns. These patterns support ongoing processes such as circulation, digestion, and hormonal regulation, all of which require consistency rather than immediacy. Despite these differences, the same foundational principles apply. Cells maintain resting membrane potentials, respond to changes through controlled ion movement, and return to balance afterward. Electrical calm precedes activity, and activity resolves back into calm. This repetition across systems highlights the unity of the body's design. The integration of electrical signaling across tissues allows for coordination without central oversight. Organs can adjust their function locally while remaining responsive to signals from the nervous and endocrine systems. This distributed control reduces strain on any single system and enhances resilience. As you rest, these electrical processes continue quietly throughout your body. Your heart maintains its rhythm, muscles hold tone without tension, glands regulate secretion, and organs adjust function gently. None of this requires awareness or effort. Electrical signaling supports the background stability that makes rest possible. In the next part of this lecture, attention will turn more specifically to the heart's electrical patterns and how rhythm emerges from cellular properties. For now, it is enough to recognize that electrical signaling is not confined to thought or sensation. It is a unifying principle of living tissue, quietly coordinating the many systems that sustain you moment by moment. 14. The heart's rhythmic electrical pattern. Among all the body's electrically active systems, the heart stands out for its quiet independence and steady reliability. It does not wait for instructions from the brain to beat, nor does it require conscious attention to maintain its rhythm. Instead, the heart contains within itself a carefully organized electrical system that generates, conducts, and regulates each heartbeat with remarkable consistency. This system exemplifies how electrical signaling can create rhythm rather than urgency, continuity rather than interruption. At rest, the cells of the heart, like other excitable cells, their interiors are slightly negative relative to the surrounding fluid, a condition sustained by selective membranes and ion gradients. Yet within certain specialized cardiac cells, this resting state is not entirely still. These cells slowly and predictably drift toward activity on their own, a property that sets the heart apart from skeletal muscle and most neurons. This gradual drift arises from the unique behavior of ion channels in these pacemaker cells. Instead of remaining fixed at a stable resting potential, their membranes allow a slow, inward movement of positively charged ions. This movement is gentle and continuous, gradually reducing the negative interior until a threshold is reached. When that threshold arrives, an electrical signal is generated, initiating a heartbeat. Once this electrical impulse begins, it spreads through the heart in an organized pattern. The signal moves from cell to cell through specialized connections that allow ions to pass directly between neighboring cells. These connections ensure that the heart muscle behaves as a coordinated whole, rather than as isolated units. The electrical wave spreads smoothly, guiding contraction in a precise sequence that supports efficient blood flow. The atria, the heart's upper chambers, receive the signal first. They contract gently, pushing blood into the ventricles below. Shortly afterward, the electrical wave reaches the ventricles, whose thicker muscle walls contract with greater force, sending blood to the lungs and the rest of the body. This sequence repeats rhythmically, beat after beat, without variation unless conditions require adjustment. Between each beat, the heart's cells return to their resting electrical state. Ion gradients are restored, membranes reset, and readiness is preserved. This recovery phase is as important as the active phase. Without it, rhythm would dissolve into irregularity. The heart's ability to reset reliably after each contraction supports its endurance over a lifetime. Although the heart generates its own rhythm, it is not isolated from the rest of the body. Signals from the nervous system and circulating hormones can influence heart rate and strength of contraction. These influences do not override the heart's electrical system, but gently adjust it. During rest, inhibitory influences slow the rate, promoting calm and efficiency. During activity or stress, excitatory influences allow the rhythm to quicken, supporting increased demand. These adjustments occur through subtle changes in membrane behavior. The fundamental pattern remains intact, but its timing shifts. This flexibility allows the heart to respond to changing conditions without losing its underlying stability. Electrical conduction within the heart is carefully channeled. Specialized pathways guide the impulse efficiently, preventing chaotic spread. This organization ensures that contraction remains coordinated rather than simultaneous across all regions. Timing, not force, is the heart's primary concern. Electrical signals shape when cells act, allowing mechanical work to unfold smoothly. The heart's electrical rhythm is also remarkably resilient. Even when isolated from the body, heart tissue can continue to beat for a time, guided by its internal properties. This resilience reflects the robustness of its electrical design, one that favors regularity and self-sufficiency. From an energetic perspective, the heart's electrical system is efficient. By relying on gradual changes and coordinated conduction, it minimizes unnecessary ion movement and conserves energy. This efficiency is essential for an organ that must function continuously, day and night, without rest. As you listen and rest, your heart continues its quiet work. Electrical signals rise and fall, chambers contract and relax, and blood moves steadily through your body. This rhythm does not compete with rest. It supports it. A calm heart rhythm reflects a balanced electrical environment, one that favors recovery and stability. The heart's electrical pattern also interacts with breathing. Slow, steady breathing influences nervous system activity, which in turn gently modulates heart rhythm. This interaction contributes to the sense of calm that accompanies rest and sleep. Electrical systems align, reinforcing one another through subtle feedback. In the broader context of the body, the heart serves as a reminder that electrical signaling need not be rapid or complex to be effective. Sometimes, its greatest strength lies in repetition and predictability. Beat after beat, the same electrical pattern unfolds, sustaining life without variation or complaint. In the next part of this lecture, attention will shift to electrical signaling in skeletal muscle, exploring how timing and coordination allow movement without strain. For now, it is enough to remain with the image of the heart's rhythm, guided by gentle electrical waves, steady and unhurried, quietly supporting you as you rest. 15. Muscle contraction and the timing of electrical signals. Movement in the body appears effortless, yet beneath every deliberate motion lies a precise and patient sequence of electrical events. They wait, holding a stable electrical state, until a signal arrives that invites them to contract. This invitation is delivered through carefully timed electrical signaling, ensuring that movement unfolds smoothly rather than abruptly. At rest, skeletal muscle cells maintain an electrical balance similar to that of neurons. Their interiors are slightly negative relative to the surrounding fluid, a condition preserved by selective membranes and ion gradients. This resting state is not one of stiffness or tension. Instead, it represents readiness, a quiet preparedness that allows the muscle to respond instantly when called upon. The signal to contract typically begins in a motor neuron. When an action potential travels down this neuron and reaches its terminal, it arrives at a specialized synapse between nerve and muscle known as the neuromuscular junction. Here, electrical signaling briefly gives way to chemical communication. The motor neuron releases a neurotransmitter into the synaptic space, and this chemical message binds to receptors on the muscle cell's membrane. This binding causes ion channels to open, allowing positively charged ions to enter the muscle cell. The membrane potential shifts, and an electrical signal is generated within the muscle fiber itself. This signal spreads across the surface of the muscle cell and deep into its interior through an intricate network of membrane invaginations. In this way, electrical change is delivered rapidly and uniformly throughout the cell. As the electrical signal travels inward, it triggers the release of calcium ions from internal storage compartments. Calcium plays a central role in muscle contraction, not by carrying electrical charge across the membrane, but by enabling interactions between the proteins that produce force. Once released, calcium binds to regulatory proteins, allowing muscle fibers to slide past one another and shorten. This shortening is the physical basis of contraction. It is controlled, graded, and reversible. The amount of force produced depends on how many muscle fibers are activated and how frequently signals arrive. Electrical timing ensures that contraction is neither excessive nor insufficient. Each signal contributes to movement in proportion to need. Importantly, contraction is not a permanent state. Almost as soon as it begins, processes are already underway to bring it to an end. Calcium is actively transported back into storage, ion channels close, and the muscle cell's membrane potential returns to its resting state. The muscle relaxes, lengthening smoothly and preparing for the next signal. This cycle of contraction and relaxation can repeat many times, guided by electrical signals that arrive in carefully regulated patterns. Rapid sequences of signals produce sustained contraction, while isolated signals produce brief movements. The nervous system adjusts timing continuously, matching muscle activity to intention and circumstance. Electrical signaling also allows for coordination among multiple muscles. Complex movements require some muscles to contract while others relax. This coordination depends on precise timing, with excitatory signals activating certain motor neurons and inhibitory signals preventing activity in others. The result is fluid motion rather than rigid action. At the cellular level, muscle fibers are organized into units that respond together. Motor neurons branch to innervate multiple muscle cells, forming motor units. When a motor neuron fires, all fibers within its unit contract simultaneously. By recruiting different numbers of motor units, the nervous system adjusts force smoothly rather than in sudden jumps. Electrical signals also play a role in maintaining posture and muscle tone. Even at rest, low-level electrical activity keeps certain muscles partially engaged, supporting the body against gravity. This activity is minimal and often unnoticed, yet it reflects ongoing communication between nerves and muscles. The balance between excitation and inhibition ensures that tone is sufficient without becoming tiring. During rest and sleep, muscle electrical activity decreases. Inhibitory influences become more prominent, reducing spontaneous contractions and allowing muscles to relax fully. This reduction supports recovery, allowing energy stores to replenish and cellular maintenance to occur. Muscle cells are resilient, designed to handle repeated electrical stimulation over long periods. Their membranes and ion channels adapt to activity, maintaining stability even during prolonged use. When activity exceeds capacity, subtle changes in electrical responsiveness signal fatigue, encouraging rest before damage occurs. In this way, electrical signaling supports not only movement, but protection. From a broader perspective, muscle contraction illustrates how electrical signals translate intention into action. A thought or reflex becomes an electrical pattern. That pattern reaches muscle, and physical movement follows. Yet at no point does this process feel abrupt or mechanical. It unfolds smoothly, guided by timing rather than force. As you rest now, your muscles are largely quiet. Electrical signals maintain minimal tone, holding posture gently without effort. Calcium remains stored, fibers lengthened, membranes stable. This quiet state is not absence, but readiness, preserved by the same principles that allow movement when needed. In the next part of this lecture, attention will turn to how electrical signals carry sensory information from the body to the nervous system, shaping perception without strain. For now, it is enough to remain with the understanding that muscle movement depends on precise electrical timing, a calm conversation between nerve and fiber that allows action to emerge smoothly and return to rest just as easily. 16. Sensory signals. Entering the nervous system. Long before awareness takes shape, the body is already listening to itself and to the world around it. Sensory signaling is the quiet process by which physical events are translated into electrical language, allowing the nervous system to remain informed without being overwhelmed. This translation unfolds continuously, even during rest, providing a steady background of information that supports balance, orientation, and safety. Sensory cells begin in a resting electrical state, much like neurons and muscle cells. Their membranes maintain a stable electrical potential, preserving readiness rather than activity. In this state, they are attentive but calm, prepared to respond only when specific conditions arise. The environment may change constantly, but sensory cells respond selectively, filtering the world through carefully tuned mechanisms. Each sensory system is specialized for a particular type of stimulus. Some respond to mechanical forces such as pressure, stretch, or vibration. Others respond to chemical changes, temperature shifts, or light. Despite these differences, the underlying principle remains the same. A physical stimulus alters the behavior of ion channels in the sensory cell's membrane, leading to a change in electrical state. When the skin is touched, for example, tiny deformations in the tissue affect mechanosensitive ion channels embedded in sensory nerve endings. These channels respond by opening briefly, allowing ions to move across the membrane. This movement produces a small electrical change known as a receptor potential. Unlike action potentials, receptor potentials are graded, meaning their size reflects the strength of the stimulus. A light touch produces a small change, while firmer pressure produces a larger one. These graded electrical changes remain local at first. They do not immediately become traveling signals. Instead, they spread gently across the membrane, influencing nearby regions. If the change is sufficient and reaches a threshold, it triggers an action potential in the associated sensory neuron. In this way, sensory systems preserve sensitivity without constant firing. Temperature-sensitive receptors operate in a similar manner. Ion channels within these cells respond to warmth or cold by altering their permeability. The resulting electrical changes convey information about temperature without requiring conscious effort. This information helps regulate behavior and physiology, guiding responses such as adjusting posture, clothing, or blood flow. Chemical senses such as taste and smell rely on receptor cells that bind specific molecules. When a molecule binds, it initiates a cascade of events that ultimately changes ion flow across the membrane. These changes are translated into electrical signals that travel to the brain, where they are interpreted as flavor or scent. Even here, electrical signaling remains restrained, reflecting concentration and relevance rather than sheer presence. Vision offers another refined example. Light striking the retina does not excite cells in the conventional sense. Instead, it alters ion channel behavior in a way that reduces activity under certain conditions. This inversion highlights the flexibility of sensory electrical signaling. What matters is not whether activity increases or decreases, but how changes are patterned and interpreted. Sensory signals often travel along dedicated pathways to the central nervous system. These pathways preserve information about location, intensity. The organization ensures that signals remain distinct, preventing confusion between different sources. As signals ascend, they may be refined further through inhibitory and excitatory interactions, enhancing contrast and clarity. Importantly, not all sensory information reaches conscious awareness. Much of it is processed at lower levels, guiding reflexes and adjustments without entering attention. Electrical signals from sensory receptors may influence posture, balance, or internal regulation quietly and efficiently. This background processing supports stability and frees awareness from unnecessary detail. During rest and sleep, sensory signaling does not cease. Instead, its influence shifts. Thresholds may rise, making cells less responsive to minor stimuli. Inhibitory influences become more prominent, reducing the likelihood that sensory input will trigger widespread activity. This adjustment protects rest while maintaining the ability to respond to significant changes. Pain perception illustrates the protective role of sensory electrical signaling. Specialized receptors respond to potentially damaging stimuli, producing electrical changes that signal threat. These signals are prioritized, ensuring that the body responds appropriately. Yet even here, modulation occurs. During rest or focus states, inhibitory pathways can reduce pain signaling, illustrating again the balance between sensitivity and calm. Electrical signaling in sensory systems also adapts over time. Continuous stimulation often leads to reduced responsiveness, a process known as adaptation. Ion channel behavior adjusts, diminishing electrical response to constant input. This adaptation allows the nervous system to remain sensitive to change, rather than being distracted by constancy. The hum of a room fades from awareness, while a sudden sound draws attention. From a cellular perspective, sensory signaling is efficient. Receptor cells convert physical energy directly into electrical change, minimizing steps and conserving energy. Once the signal has been conveyed, systems reset quickly, restoring readiness without lingering excitation. As you rest, sensory receptors throughout your body are active at a low level. They monitor temperature, pressure, and position, sending gentle electrical updates that support comfort and balance. Most of these signals never reach awareness, yet they contribute to the sense of ease that accompanies rest. In the next part of this lecture, attention will turn to how electrical activity changes during rest and sleep, exploring slower rhythms and coordinated quiet. For now, it is enough to remain with the understanding that sensory electrical signaling is not intrusive or demanding. It is a background process, translating the world into gentle electrical patterns that inform without disturbing, allowing awareness to soften while the body remains quietly attentive. 17. The nervous system at rest and during sleep. As activity quiets and attention softens, the nervous system does not switch off. Instead, it enters a different mode of electrical organization, one shaped by slower rhythms, broader coordination, and an emphasis on restoration. Rest and sleep are not absences of signaling, but carefully regulated states in which electrical activity becomes more synchronized and restrained, supporting recovery without losing awareness entirely. When the body begins to rest, changes unfold gradually. Inhibitory influences increase, reducing the likelihood that neurons will respond to minor stimuli. Excitatory signals do not disappear, but they become more selective. This shift protects the resting state, allowing the nervous system to disengage from constant responsiveness while remaining capable of reaction if needed. Electrical patterns within the brain also change. During waking activity, neurons often fire in complex, desynchronized patterns that support perception, movement, and thought. As rest deepens, these patterns give way to slower, more rhythmic activity. Groups of neurons begin to synchronize, producing waves of electrical activity that reflect shared timing rather than isolated signaling. These rhythms are not imposed from outside. They emerge naturally from interactions among neurons and their intrinsic properties. Slow rhythms are especially prominent during sleep. In these states, large populations of neurons alternate between periods of activity and quiet. These alternations unfold gently, creating oscillations that sweep across regions of the brain. Rather than carrying specific messages, these rhythms support global processes such as memory consolidation, metabolic restoration, and the regulation of internal balance. At the cellular level, neurons during sleep continue to maintain their resting membrane potentials. Ion gradients remain intact, membranes selective, and channels responsive. What changes is the pattern of activation. Signals become less frequent and more coordinated, allowing cells to rest without losing readiness. This balance ensures that sleep is both deep and safe. Inhibitory neurotransmitters play a central role in shaping sleep-related electrical activity. Their increased influence dampens spontaneous firing and promotes synchronization. Excitatory neurotransmitters remain present but are modulated, preventing excessive activation. Chemical and electrical signaling work together, adjusting tone rather than enforcing silence. Sleep also involves shifts in modulatory systems. Neurotransmitters that promote alertness decrease in influence, while those supporting rest become more prominent. These changes alter the electrical responsiveness of neurons across the brain, favoring stability and slow rhythms. Importantly, these shifts are reversible. As waking approaches, modulatory influences adjust again. Electrical activity during sleep is not uniform. Different stages are characterized by distinct patterns. Lighter sleep involves modest slowing and increased synchronization, while deeper sleep features more pronounced slow waves. Even in the deepest stages, brief bursts of activity appear, reflecting ongoing processing rather than complete inactivity. These electrical patterns support essential functions. Memory traces formed during waking are revisited and reorganized, guided by coordinated activity across brain regions. Metabolic waste products are cleared more efficiently, aided by changes in blood flow and cellular activity. Electrical calm provides the conditions necessary for these processes to unfold without competition from external demands. Restful states outside of sleep share some of these features. Quiet wakefulness often involves reduced sensory processing and slower electrical rhythms, though not to the same extent as sleep. In these states, awareness may remain present while activity softens. The nervous system balances openness with restraint, allowing rest without loss of orientation. Importantly, the transition into and out of sleep is gradual. Electrical patterns shift smoothly rather than abruptly. Neurons adjust their activity in response to changing chemical signals and internal conditions. This gradualism protects stability, preventing sudden changes that might be disruptive. The body's electrical systems also coordinate during sleep. Heart rhythm slows slightly, breathing becomes more regular, and muscle tone decreases. These changes reflect shifts in nervous system signaling, favoring parasympathetic influences that support rest. Electrical calm spreads across systems, aligning them toward recovery. Even during sleep, the nervous system remains attentive to certain signals. Sensory thresholds are higher, but not absolute. Significant stimuli can still trigger electrical activity, prompting awakening if necessary. As you listen and rest, your own nervous system may already be shifting toward these patterns. Electrical activity softens, rhythms slow, and coordination increases. Neurons communicate less frequently but more synchronously, supporting a state of ease. In the next part of this lecture, attention will turn to how electrical signaling adapts over the lifespan, changing gently from development through maturity. For now, it is enough to remain with the understanding that rest and sleep are active states, guided by calm electrical rhythms that sustain balance, restore function, and allow the nervous system to renew itself quietly and continuously. 18. Lifelong electrical activity and gentle adaptation over time. From the earliest moments of development through the quiet years of maturity, electrical signaling in the body is never fixed. It changes gradually, adapting to growth, experience, and age without losing its fundamental structure. These changes do not represent decline or instability, but refinement. Electrical systems evolve with the organism, adjusting their rhythms, thresholds, and patterns to support each stage of life. In early development, electrical activity plays a formative role. Even before complex structures are fully established, cells exhibit electrical properties that guide organization and differentiation. Subtle differences in membrane potential influence how cells divide, migrate, and specialize. These early electrical cues help shape tissues and networks, quietly guiding growth long before conscious experience emerges. As the nervous system develops, electrical signaling becomes more structured. Neurons extend their projections, form synapses, and begin to communicate through coordinated activity. In these early stages, electrical patterns are often more spontaneous and variable. Activity helps refine connections, strengthening some pathways while allowing others to fade. Through this process, experience, and environment shape the emerging system, guided by electrical responsiveness rather than rigid instruction. During childhood and adolescence, electrical signaling continues to mature. Myelination increases. Synaptic connections are pruned and refined, enhancing clarity and reducing unnecessary activity. Thresholds adjust, inhibitory systems strengthen, and balance becomes more stable. These changes support the development of coordinated movement, attention, and emotional regulation. Importantly, this maturation unfolds gradually. Electrical systems do not leap from one state to another. Instead, they shift incrementally, guided by activity patterns and internal cues. This gradualism preserves stability, ensuring that growth does not disrupt function. In adulthood, electrical signaling reaches a relatively steady state. Patterns of activity reflect established networks, shaped by learning and habit. Balance between excitation and inhibition is maintained efficiently, supporting both responsiveness and rest. Electrical rhythms during sleep and waking become consistent, reflecting a system that has learned how to regulate itself. Even in this apparent stability, adaptation continues. Electrical properties remain sensitive to experience. Learning, practice, and environmental change can still alter synaptic strength and network organization. These changes tend to be more subtle than in early life, but they are no less meaningful. The nervous system retains its capacity to adjust, guided by the same electrical principles that shaped its development. As age advances, electrical signaling continues to adapt. Some changes reflect shifts in cellular metabolism and structure. Ion channel expression may alter slightly, and conduction speed may change modestly. These adjustments are often gradual and compensated for by network-level adaptations. The system emphasizes efficiency and reliability, maintaining function through balance rather than speed. Importantly, many aspects of electrical stability are preserved throughout life. Resting membrane potentials remain intact, synaptic communication continues, and rhythmic activity during rest and sleep persists. While patterns may slow or simplify, the underlying structure remains sound. The nervous system prioritizes continuity, ensuring that essential functions are maintained. Changes in electrical signaling with age often reflect a shift toward conservation. Thresholds may rise slightly, reducing responsiveness to minor stimuli. Inhibitory influences may become more prominent. These changes can contribute to a greater sense of steadiness, aligning electrical activity with the body's evolving needs. The adaptability of electrical systems also supports recovery and compensation. When injury or illness alters certain pathways, others can adjust, taking on additional roles. Electrical signaling supports this flexibility by allowing networks to reorganize gradually, guided by use and experience. This capacity does not vanish with age. It simply unfolds more slowly. Across the lifespan, sleep continues to play a central role in maintaining electrical balance. Restorative rhythms support repair, integration, and metabolic regulation. Even as patterns change subtly over time, sleep remains a cornerstone of electrical stability, providing regular opportunities for recalibration. From a broader perspective, lifelong electrical activity reflects a design that favors persistence over perfection. Systems are built to endure, adjusting gently rather than failing abruptly. Electrical signaling supports this endurance by allowing cells and networks to remain responsive while protecting them from overload. As you rest and listen, your own electrical systems reflect this history of adaptation. Every neuron carries patterns shaped by development, experience, and time. These patterns do not demand attention. They simply persist, supporting awareness, movement, and rest in quiet continuity. In the final part of this lecture, attention will turn to how all these electrical processes come together as a single, integrated system, sustaining life as a continuous conversation rather than a series of events. For now, It is enough to remain with the understanding that electrical signaling is not static or fragile. It is resilient, adaptive, and enduring, quietly evolving with you across the unfolding of a lifetime. 19. One continuous electrical conversation within the body. When all the elements of electrical signaling are considered together, a single unifying picture begins to emerge. Rather than a collection of isolated systems, the body reveals itself as a continuous electrical conversation, unfolding moment by moment across cells, tissues, and organs. Each signal, whether large or small, brief or sustained, participates in this conversation, contributing to coherence rather than noise. At the foundation of this continuity lies the resting electrical state of cells. Every cell maintains its membrane potential, holding a quiet readiness that makes communication possible. This shared baseline allows diverse tissues to participate in the same fundamental language. Neurons, muscle cells, glandular cells, and sensory receptors all speak through controlled changes in electrical charge, guided by membranes, ions, and carefully regulated channels. Signals begin locally, shaped by immediate conditions. A sensory receptor responds to pressure. A pacemaker cell in the heart drifts toward activity. A neuron integrates synaptic input. These local events are not isolated. They influence neighboring cells through direct connections, chemical messengers, or shared rhythms. In this way, small electrical changes can ripple outward, becoming part of larger patterns. The nervous system serves as a central coordinator, but not a dictator. It integrates electrical information from the body and distributes influence in return, adjusting tone and timing rather than issuing commands. Autonomic pathways modulate heart rate, digestion, and glandular activity through gentle shifts in electrical responsiveness. Voluntary pathways coordinate movement through precise timing. In both cases, control is exercised through modulation rather than force. Chemical signaling weaves seamlessly into this electrical fabric. Neurotransmitters, hormones, and local messengers adjust how cells respond to electrical change, altering sensitivity and timing. These chemical influences do not replace electrical signaling, they enrich it. By shaping thresholds and rhythms, chemical signals allow the electrical conversation to adapt to context and need. Across the body, rhythms emerge from this interplay. The heart beats in steady cycles, guided by intrinsic electrical patterns and refined by nervous input. Breathing follows its own rhythm, coordinated with heart rate through shared electrical influences. Sleep introduces slower rhythms that synchronize large populations of neurons. These rhythms do not compete. They align, forming layers of timing that support stability. Importantly, the electrical conversation is bidirectional. Signals travel from the body to the brain and back again. Sensory information informs posture and balance, while motor commands shape movement. Internal states influence perception, and perception influences internal states. Electrical signaling allows these exchanges to occur rapidly and continuously, maintaining integration across distance. This integration supports adaptability. When conditions change, electrical patterns adjust. Increased activity shifts rhythms and thresholds. Rest restores balance. Learning reshapes synaptic connections, altering future responses. Injury prompts reorganization, allowing remaining pathways to compensate. Throughout these changes, the conversation continues, guided by the same principles of balance and restraint. The continuity of electrical signaling also supports resilience. Because communication is distributed, no single point of failure can disrupt the entire system easily. Local disturbances are often contained or compensated for by adjustments elsewhere. Electrical calm provides a buffer, allowing the body to absorb change without losing coherence. At the experiential level, this continuous conversation underlies the sense of being a unified self rather than a collection of parts. Awareness feels seamless because the electrical systems that support it are integrated. Movement feels coordinated because signals arrive at the right time. Rest feels restorative because rhythms align toward calm. Even during stillness, the conversation does not stop. Electrical signals maintain posture, regulate circulation, and support internal balance. The absence of conscious activity does not imply silence, but a shift towards slower, more coordinated patterns. The body remains quietly engaged in maintaining itself. As you rest now, this conversation continues without effort. Cells hold their potentials. Signals arise and resolve. Rhythms unfold. There is no need for intervention or attention. The system is designed to sustain itself through balance rather than control. In the final part of this lecture, attention will gently return to a broader perspective, reflecting on how this quiet electrical harmony supports life as a whole. For now, it is enough to remain with the understanding that within you exists an ongoing electrical dialogue, continuous, adaptive, and calm, sustaining each moment with quiet precision. 20. A calm closing reflection on the body's quiet electrical harmony. As this lecture gently comes to rest, it is helpful to step back and hold the entire picture of electrical signaling in the body as a single, continuous presence. From the smallest cellular boundary to the broad rhythms of organs and systems, electrical activity unfolds without urgency. Nothing needs to be added, accelerated, or corrected. The system already knows how to hold itself. Throughout the body, electrical signals do not exist to impress or overwhelm. They exist to coordinate, to align, and to maintain continuity. Every cell preserves its electrical readiness, every membrane maintains its selective boundary, and every signal rises only when conditions quietly invite it. Activity emerges naturally from rest, and rest always follows activity, restoring equilibrium with patient consistency. This rhythm of emergence and return is not confined to the nervous system. It is reflected in the beating of the heart, the movement of muscles, the regulation of glands, and the slow adjustments of internal organs. Each system participates in the same electrical language, adapted to its own tempo and purpose, yet unified by shared principles. Separation allows difference, difference allows potential, and potential allows communication. What makes this electrical harmony especially remarkable is its invisibility. You are not required to monitor it, guide it, or understand it for it to function. It unfolds beneath awareness, freeing attention to drift, soften, and eventually fade into rest. Even when consciousness quiets, electrical balance remains, sustaining the body without interruption. In moments of stillness, the nervous system gently withdraws from constant engagement. Thresholds rise, rhythms slow, and signals synchronize. Electrical activity becomes broader and calmer, supporting restoration rather than response. This shift is not a shutdown, but a reorientation, allowing maintenance and integration to take precedence over interaction. Sleep, in this sense, is not an escape from electrical activity, but a refinement of it. The same systems that support alertness and action now support recovery and coherence. Neurons fire less often, but more together. Chemical influences favor calm. Electrical waves slow and deepen. The body remains attentive, yet undisturbed. Across a lifetime, these patterns adapt and endure. Electrical signaling evolves gently with growth, learning, and age, preserving function through flexibility rather than rigidity. Change is absorbed gradually, balanced by continuity. The body does not rush toward the future. It carries its past forward in the form of stable rhythms and learned patterns. This continuity is perhaps the most calming aspect of the body's electrical nature. Nothing is required of you for it to persist. You do not need to hold posture consciously. regulate your heartbeat, or guide sensory processing. Electrical systems handle these tasks quietly, sustaining a sense of safety that allows rest to deepen. As you listen, your own body reflects this harmony. Signals travel where needed and pause where not. Cells maintain their charge, membranes their selectivity, and systems their rhythm. There is no competition between parts, no urgency to resolve. Everything unfolds at its own pace, guided by balance rather than demand. In understanding this, there is an opportunity to let go. The body is already doing what it needs to do. Electrical calm does not depend on effort, attention, or intention. It arises naturally from the structures and processes that have been shaped over time to favor stability and resilience. The idea of the body as an electrical system need not feel technical or abstract. At its core, it is simply a story of quiet coordination, of small differences held patiently, of readiness without tension, of movement that emerges only when invited and resolves as soon as it has served its purpose. As this lecture draws to a close, there is nothing left to learn or remember. The concepts have already returned again and again in gentle variation. Cells hold charge, signals move smoothly, balance is preserved, rest is active, and activity returns to rest. These truths are already present within you, expressed continuously in the language of your own body. You may notice that as attention softens, awareness of these ideas fades into background understanding. Just as electrical signals give way to calm once their role is complete, so too can thoughts settle without needing resolution. The body will continue its quiet electrical conversation whether you remain awake or drift toward sleep. Signals will rise and fall, rhythms will align, and balance will be maintained. There is nothing further to do. In this way, the study of electrical signals in the body returns naturally to the experience of rest. And the steady, gentle harmony within continues, supporting you quietly, moment by moment, as awareness softens and rest deepens.